We have two sort of pillars of 20th century science. There's quantum mechanics, which is the study of things that are extremely small, but it's a phenomenally successful theory. It can predict detail, well, it makes all more modern electronics possible. We can predict the light emission from light bulbs to fantastic accuracy. And then there's Einstein's theory of general relativity theory, which is extremely successful, describing things like the Big Bang theory, the evolution of the universe, black holes, neutron stars, everything to do with gravity. So we're thinking of very big things with lots of gravity.
Quantum mechanics actually began to develop in the early 20th century, actually around the same time that Einstein was developing relativity. In fact, he was one of the people who also worked on quantum mechanics and laid the foundations. And one of the interesting things that we learned in quantum mechanics from the work of many people besides Einstein who developed the theory further was that time in quantum mechanics is also much more interesting than you may have thought, and space as well.
What quantum mechanics tells you is that when a process occurs, there's a probability it'll go one way or probability it'll go another way. And there are two competing interpretations. There's the classic interpretation called the Copenhagen interpretation, which says, well, when somebody observes the universe, or observes the outcome, it collapses into that state and you lose all knowledge, all possibility of the other thing being real. Then there's the many worlds interpretation of quantum mechanics. I think goes back to Everett and Wheeler. Basically, the idea is that when a quantum process happens, there are two possible outcomes. There's a sort of splitting of the universe or splitting of worlds, and there is a world where one thing happens and it's been observed to happen. There's a world where the opposite thing happens, and the observers all say that opposite thing happened.
For example, the famous example that we always use is Schrodinger's cat. We have a cat in a box, and the box is hooked up to some radioactive quantum mechanical substance that will kill the cat with a 50-50 chance. So in ordinary classical physics, what we would say is there's a box, and inside there's either an alive cat or a dead cat. We don't know which one. In quantum mechanics, that's not true. In quantum mechanics, we say in the box, there's a cat, and there's a 50% of the cat that is alive, and there's a 50% of the cat that is dead. And it's just not true that there is a state of affairs, that there's a fact of the matter about the life or death of the cat. It's in a superposition. There are, in fact, two different versions of reality that are simultaneously true, with the cat being alive and the cat being dead. When you have not yet looked at the cat, those different versions are there in the box, but they haven't impacted your outside world yet. When you open up the box and look at the cat, there's now a world in which you see the cat alive, and there is a world in which you see the cat dead.
And so at every quantum decision, if you like, there's a splitting of the universes, and so every possibility plays out in some, in this sort of branch tree of all possibilities.
So that opens up a whole new world of possibilities for time travel if you couple the already implausible idea of traveling backwards in time with the extra implausible idea of traveling to a different universe.
This quest to put together two of 20th century's most important physics outputs, which is general relativity and quantum mechanics, and make them work together, that's the quest for something we call quantum gravity.
These two theories of physics are incompatible with each other, so something has to give.
But both theories are correct at some level. So the question is, can you patch those together? The answer seems to be yes, and we've only figured this out in the last 20, 30 years, but the answer seems to be yes. It's called string theory.
And it sort of makes you wonder, why is something called string theory have anything to do with gravity and quantum mechanics? And it's actually a really simple idea. It was back in the 60s, people were trying to understand tiny subatomic particles, and they noticed that if you took two of these particles and stretched them, they didn't separate. Rather, they created two new particles in between them. So it was almost like you take a piece of string and you cut it. You never end with a piece of string that only has one end, because you've created two new ends by cutting it. Every little piece of string has two ends. So some clever person says these elementary particles are acting like they are ends of a piece of string.
And then that string can vibrate, and it can wrap around things, etc. And that vibration and wrapping around things is a new feature that the theory has that actually allows, at least on paper, to address a number of problems that we had no idea how to address by just working with particles. And so that's why the theory is very promising.
The difficult part of it is it's very difficult to connect it to the real world. That's not to say it can't be, but we haven't gotten there yet. We're trying. If we ultimately want to understand, is time travel possible? Is wormholes possible? Is negative energy possible? You need to marry together gravity and quantum mechanics, which means that string theory might be the necessary ingredient.
It's already beginning to allow us to explore questions in gravity that we weren't able to explore using Einstein's theory alone. For example, when you put quantum mechanics together with the physics of black holes, as Hawking and others did, you begin to see that black holes are much richer internally than you may have thought.
There's a much richer structure that you can put in the interior of a black hole. The structure of the black hole inside is a much more answerable question in string theory.
We'll be able to, if things work out, answer some of these issues about can we make the kinds of spacetimes we need? Are they stable spacetimes, for example? In Einstein's theory, typically, it's very difficult to make a wormhole and then have it stay open, that you can traverse it. Perhaps there are effects that are not accounted for in Einstein's equations that can help you hold these things open.
We normally think of physics as you do an experiment and see who's right. We can't do experiments that test string theory yet. But we can and have found some remarkable spin-off technologies that have told us things that we may not have expected to be told. It's been an incredible experience in this respect.
We're a long way from answering any of these puzzles using string theory, but it certainly seems to have the right seeds for at least having a go at doing it.